Section 3.2, we are now moving into comparing rates. So this allows us to change the time period in our exponential models. In the last section, we were talking about something maybe doubling every hour, and so the time period in that case is 1 hour. But more generally, we're often talking about time periods. Maybe it's 5 hours, maybe it's 20 minutes, maybe it's a half an hour. And you want to be able to reconstruct the form for your model in order to accommodate a different time period. So that's what we're focusing on in 3.2. We'll start with an example. If you are given a growth factor that's 20% every 20 minutes, so really that's a growth rate, but your growth factor in that sense will now be 1.2, remember, if we think about what we talked about in 1.1, or 3.1, sorry. What is the growth factor every hour? So this is the growth factor every 20 minutes, which means that we then have to write the 20 minutes in terms of hours. So 1 hour is 60 minutes, right? Which means that we have 3 20-minute intervals that compose a full hour. So if we're trying to find the growth factor for every hour instead of every 20 minutes, then we're going to have to take a look at going back to first our exponential model, right? F of x equals c times a to the x. If we assume that c equals 1, we can really focus on our growth factor on its own and look at just a to the x, because that's what we want to modify. We want to modify a so it's consistent for an hour instead of 20 minutes. Now, if we have 3 20-minute increments in an hour, then whatever a was for the 20-minute interval will be cubed for the hourly growth factor. Why, you might wonder? So if I have an a to the x and I have 3 time periods, then I'm going to end up with a 3 in the exponent, right? Where my x is up here, I'm going to end up with 3 of them to correspond with an hour instead of just 20 minutes. So I'm not going to just multiply my answer by 3, I'm going to change my exponent in order to be consistent. So for this particular problem, a is 1.2, because if it's growing by 20%, our a is 1 plus the 0.2, which gets us a 1.2. And a cubed is 1.2 quantity cubed, which is 1.728. So our growth rate in 20 minutes was 0.2, but our growth rate for hourly is 0.728. Notice that we didn't just get 3 times what our 20-minute was, right? This is not 0.6. This is 0.728. So it's actually a little bit faster because it compounds, because we're dealing with an exponential model and not a linear model. So this isn't just going to triple. But our exponent, we will cube our growth factor in order to determine the new rate. If we want to go the other direction, we can look at an example here. If a virus is replicating at a rate where it is currently tripling itself every 5 hours, but we initially have 10 copies, then we can model the every 5-hour increment in the same way that we were talking about in the last section, where we just have our initial value of 10 times our triple, which is a 3, to the x. But notice that this is a model for the number every 5 hours, so it's in an increment where x is given every 5 hours. So 1x corresponds to 1 5-hour increment. Now, if we want to find the model for every hour, this is going the opposite direction. We now have 5 hours going down to 1 hour. Then we need to have an exponent that decreases, and specifically for this one, we're going from 5 to 1. If we go from 5 to 1, we have to divide by 5. So our exponent, we get an extra 1/5 up here that corresponds to going from 5 hours to 1 hour. So I have a note here, right? If x is in 5-hour increments, and we want our new x, which I'm calling x bar, just so that it's somewhat different, and we want that in 1-hour increments, I know that x bar is going to equal x divided by 5, right? If I divide both sides of this by 5, I'll end up with 1 hour, where I currently have 5 hours. So x over 5, which tells me that I want to have that extra 1/5 in my exponent in order to accommodate that change. So this is how you're going to convert algebraically, so you can change the exponent to be consistent. That's the key thing here, is checking, is this consistent? Because if I substitute in 1 into my every 5 hours equation, I'm going to change the color so it's a little bit more obvious what I'm doing. Right, if I put that in here, then the 1 corresponds to 5 hours. And in order to get the same thing, I have to plug a 5 into this equation in order for that to work. And that's the key, right? This is every hour, and this was every 5 hours. So for one 5-hour increment, I plug a 1 in to the green, and I would plug a 5 in to the orange to get the same value. And I should get the same value because it's the same model. I just converted the time period. An application of this same concept is investments. So specifically, we're going to be looking at the compound interest model. And we will actually do a lot of interest models. So you will have about 4, I think, to compare against, and you will get a formula sheet, but you want to make sure that you really know what the heck this means. So for now, we'll focus on the compound interest model, where the value of the amount that you have put into an account. So say you put money into a high interest bank account and it has compound interest, then A corresponds to the amount of your investment after so much time. So that is both your principal and your interest, not just your interest in this case. P is the principal balance. That's however much money you initially put into it. R is the interest rate on the account. N is the number of times that interest is applied every year, because generally this entire model is set around number of years. So T is therefore time in years in order for that to be consistent. This relates back to our exponential model from before, because we have a growth factor just like we did before, and A being raised to the power, in this case t instead of x, but again for time, A is that 1 plus r over n raised to the nth power. It looks just like that c a to the x, it's just c has been replaced with p and x has been replaced with t. That's it. So this is a lot like the growth factor from before, and that a equals p times a to the t is what it would look like. So our growth rate is going to be what we will now call the annual percentage yield, and that is that a value, which is 1 plus r over n raised to the nth power, minus a 1. That gets us our annual percentage yield. And this is something that you've probably heard before as APY, which is why I wrote APY here. So you've probably heard of it before, maybe a commercial about selling a car or something, you would have heard of this in that, but it's really corresponding to that growth rate in terms of that compound interest. So let's look at an example of this interest model. If you invest $5,000 into a high interest account that pays 4% annually, but it's compounded monthly, determine a model for the interest accrued each month. So in this particular case, we have principal of $5,000. We have an interest rate of 4%, so that's the 0.04 for R. We know it's compounded monthly, and there are 12 months in a year, so n is equal to 12. It will be compounded 12 times over the course of the full year. And now, there's some important distinctions here. One of the things is I said each month. Now, each year, we just plug things in. So, this model's per year. We have A of t equals p times 1 plus r over n to the nt. That's 5,000 times 1 plus 0.04 over 12 raised to the 12t. So this model, that is the equation that you have, gives you a model per year. So whatever I substitute in for t will correspond to years. This is your go-to default starting point right here. Okay? Now, I said per month. That's going to be a little bit different. All that it changes, though, is the exponent. Everything else will remain the same. Per month means that instead of accumulating this 12 times per year, right, so I multiply by 12 up here in my exponent, I'm just not going to do that for per month. Per month I have the exact same form, except there's no n in the exponent. Because if it's per month, if I do this 12 times, I will hit a year, and that will correspond to the 12t that I have in the exponent. So if I ask you the question, how much interest accrues after 5 years, you can see this directly. If we use the per year model straight out with the formula, we have 5,000 times 1 plus 0.04 over 12 raised to the 12th power times the 5 years. Right? So that puts us at 5,000 times about 1.0033 raised to the 60th power, which, when you simplify, gets you $6,104.98. Remember what I said? This is the principal plus the interest. This is not just the interest. So your interest is found by subtracting subtracting P from A. So your principal balance off of that, which leaves you with about $1,104.98 in interest from that accrual over those 5 years. Notice that this will be exactly the same as if I use the per month example and substitute in 60 for t. 60 months, which is what I got up here, is exactly the same as what I get over here. And so all I'm trying to do is just explain what is happening with those different time periods, right? If it's per month, it's one thing. If it's per year, it's another thing. So you just want to be very, very aware of what is being asked for, because it is going to change the equation significantly. As another little aside, just for you to think about, if this interest accrued daily instead of monthly, how much interest would accrue in 5 years? So what kind of the underlying question here is, will I have more interest or less interest if I accrue daily instead of monthly? So daily, I now have to divide by the number of days in a year, 365, and for the yearly model, I end up with that 365 in my exponent, right? So over 5 years, I would just substitute in 5 into my yearly model, and I would get $6,106.95. Again, I subtract the principal, and I have $1,106.95. Whereas with monthly, it was $1,104.98. So the difference is not very much, but you can see that you get a little bit more interest the more frequently you accrue it. So daily, if you want to earn more interest off of your own money, is fantastic. It's a difference of $1.97. It's not a huge difference. But long term, that would add up significantly. So it does make more sense that if you want more money, to accrue it more frequently. However, as you can see, it doesn't make a huge difference in your overall interest value. And if you have any questions, let me know.